I will start here with my lab 5 presentation. So the purpose of this lab would be to predict the motion of a slinky and see if the bottom stays motionless or if it'll fall to the ground. Some of the fundamental principles we'll be using is Newton's second law, energy principle, along with some spring principles. The system for this lab will be the slinky, and the surroundings will be the earth and everything else. And a little preview for the results, we'll be able to predict the motion of the system, which will be our slinky. Some of the physics and equation we'll be using is when we're going to have to use the force of gravity, because there's obviously going to be gravity acting on the slinky, which is our spring in this lab. We'll also have to use our position update formula and our velocity update formula to calculate the velocity position for our models and other stuff. And Fs, that's our spring force, because we have to calculate our spring force acting on the slinky. And then we also have the force of drag in this right here, which we have RB, which we multiply by the magnitude of the ball's velocity times, which is squared, times the normal of the ball velocity to get our direction. In the experiment, our initial conditions, our time will be 29.76 seconds, with our initial velocity being 0. Our initial position is 1.236 meters, which that is the difference in the top and bottom of the slinky. So we can see that our initial position is just how far the top of the slinky is from the bottom. Our G is 9.8 due to gravity, with mass being 0.25 kilograms, and our K, which is for our spring constant, will be 4.5. And we can see the experiment. We see here at the slinky drop. And see the bottom state motionless in that. So we use the tracker to analyze that. But other than the tracker data, we also got data from our code. Now, if we look, we put in all of our initials on this left side of it, put in our G or J, our velocity, position, everything. Now we can see what we did. Well, we calculated our work in the force of drag using these equations right here. And then we used also our force of the spring, calculated that all into the F net. All right. And then what we're calculating here is the difference in the bottom of the slinky and top of the slinky. So we can see how that difference changes. And as we can see in both graphs, the difference in the spring from top to bottom went to 0, which means the bottom had to have stayed in place. So the bottom stayed in place because the force of gravity was counteracted by the force of the spring back up. Therefore, the bottom stayed motionless until the slinky, the difference in it became 0, where it hit each other. As you can see, the glass are very close with the same screen. Obviously, it is a little different, probably because of the low amount of data points because of the frame rate of the video. So some possible cases of error. The tracker is not 100% precise in its calculations. So if you even slightly misclick your data, technically slightly off. So that's always a miscalculation. There's could have been spring deformation, which could have very small effect, but still could have happened. And the low frame rate only gave us minimal points of data, so therefore the possible cases of error are much higher. Now, what does it mean? Why did the slinky at the bottom stay motionless? Well, because the force of the spring pulling the slinky up counteracts this gravity, making it motionless. And until that spring force comes back on itself and this two ends of the slinky touch, gravity just cannot overcome that spring force. But when they finally collide, gravity is able to overcome it, and therefore it'll put the slinky to the ground. Now, what does it mean, number two? What if the slinky was stretched a smaller height? Well, nothing would change just how long it takes the slinky to fall, as all principles previously discussed are still relevant, so therefore everything would be the same. Because if you think about it, the spring force of that slinky is still there, even if, as you can see in the video, halfway down, the slinky was still held in the air at the bottom. Because nothing really changed until both sides of the slinky are touching or together. That is when it'll actually start to fall, and the bottom won't stay hovering in the air. And that is my lab.